Now that we've talked about stoichiometry and how to use a balanced equation to determine the progress of a reaction, we're going to look at different types of reaction. In fact, we're going to get into a little more stoichiometry. Remember, when you want to go from one place to another in a balanced equation, you use moles. You've got to get moles somehow. The only example we've used so far is you start off with mass and convert to moles. But that's not the only way to get to moles. If you're talking about solution chemistry, then you've got very often moles of something dissolved in a solution, and when you mix them together, you know how many moles go into that reaction. So you use a different way to calculate, but you still have to know moles before you can move from one place to the other in a balanced equation. All right. We are interested primarily in aqueous solutions. When we talk about solutions, we mean aqueous. There are a whole host of different types of solutions, but when we put things in aqueous solution, that covers a large part of the chemistry we're interested in, particularly if you're going into life sciences. It's all aqueous for the most part. So we need to know something about the solvent, that is water. Water is a polar compound. In other words, and it's a molecular compound. Hydrogen and oxygen are sharing electrons. So each water molecule is a unique entity unto itself. And it has a shape like this. It's bent molecule. Plus, the oxygen tends to draw electrons to itself more strongly than the hydrogens do. So you get what we call a dipole. And we draw it like that, with a plus end down here showing that this is the plus end. And this is the direction that the electrons want to move. So what it does overall, and this will be the same. You know about vector addition? No, okay. Well, I'll just tell you. If you add these two vectors together, then overall for that whole molecule is that way. So for the whole molecule, you get a slight negative on this side and a slight positive on that side. That's called a polar molecule. Its polarity is instrumental. Well, it explains why water dissolves ions and other polar compounds very well. But it doesn't like nonpolar compounds, like oil. Okay? Oh, I need to get rid of that. That's based on Flash, and Flash isn't supported anymore. Sorry. So when we talk about solutions, we need to define our terms. I use terms that I didn't define yet. The solute in a solution is the substance being dissolved. And remember, solutions are homogeneous mixtures. The substance being dissolved is the solute, so it's the minor component. And the solvent is the major component, in this case, water. Now, if you dissolve something in water and it now conducts electricity, it's known as an electrolyte. And it does that because it breaks up into individual ions. Electric current will not pass through a substance unless there's something to convey the charge from one electrode to the other. So there may be ions there, but if they're fixed in place and can't move, it's an insulator, like a crystal of sodium chloride is an insulator because those sodium and chloride ions are locked in place. Now, if you melt it, which you can do if you get it hot enough, if you can melt sodium chloride, then the ions are free to move and it becomes a conductor. Or if you dissolve sodium chloride in water, then it breaks up those individual ions into solution. Now it's an electrolyte. And those individual ions will convey the charge from one electrode to the other very easily. And we can semi-quantitative, actually it's qualitative, define the difference between a strong electrolyte and a weak electrolyte. Strong electrolytes basically dissociate completely in solution and make free ions, like sodium chloride is a good example. And if you hook up a circuit with a light bulb in them and put your electrodes in the water with a strong electrolyte, then the bulb will be bright. On the other hand, if the solute is very weak in dissociation, it only makes just a few ions per mole of molecules, then it'll be a weak electrolyte and the light bulb will be very dim. Examples are some weak acids like acetic acid, like vinegar. A weak solution of vinegar will only light that bulb very dimly. Non-electrolytes, they're insulators. They will not transfer current through the solution. Example, table sugar. You can put a lot of table sugar in water. I mean, you can put so much sucrose in water, dissolve it in water to where you've got more sucrose than water eventually. But it will not conduct electricity. It doesn't form transmitting ions. Okay. So when we're discussing these reactions, we need to know something about the nature of the reaction. In general terms, what type of reaction is it? That helps us understand what's going on the microscopic level. And then we need to know something about how much of each of the chemicals that enter into that reaction, how much is in that solution. Because that will dictate what type of reaction and the extent of the reaction as well. Right? So we need some way to express concentration. And the most common way, actually the most useful way in chemistry is molarity. It's designated a large M, molarity. And by definition, molarity equals the moles of the solute, right, the minor component, per liter of the solution. So that includes both the solute and the solvent. Notice we have an equation here. Equals moles, and that's my abbreviation for moles, per volume. Whenever you have an equation, if you know all but one of the variables, you can solve for that unknown, right? If we know this one and this one, we can solve for the number of moles. If we know this one and this one, we can calculate the molarity. If we know that one and that one, we can say, this is how much volume is required to give me that many moles with that concentration. Okay? So this example says 3 molar hydrochloric acid may be produced by 6 moles of HCl and 2 liters of solution. But the ratio is the important part. You can have 3 moles of HCl and 1 liter of solution, give you the same concentration. Right? These are capacity factors. Right? This is an intensity factor. It doesn't matter how much you have, that value will always be the same. If you have a solution of 3 molar, you can take out that much of it, or you can take out that much of it. And they'll both be 3 molar concentration. Doesn't matter how much. Okay. So how do we calculate the molarity of this solution? We're given 500 grams of potassium phosphate, and the final volume is 1.5 liters. All right, go back to your formula. It has to be moles per liter. Right? Moles per liter. So do you have moles? No. You got grams. So this is where knowing how to write the formula comes in handy. Potassium phosphate. Potassium phosphate. Right? So how many potassiums do you have? Remember, this is a polyatomic ion with a 3- charge. So you need 3 of these, correct? So that's your formula unit, K3PO4. You determine the molar mass, grams per mole, and convert that grams into moles. Now you have that part of your equation. And then you're given the final volume. So you plug that in and do your calculation from there. Right? So, can't see that too well, can we? So here's the molar mass of potassium phosphate converted to this many moles. Divide that by 1.5 liters, and our solution is 1.57 molar, which is concentrated. That's a pretty high concentration. Now, that was potassium phosphate. That was the whole formula unit. I was about to say molecule, but it's not a molecule. The whole formula unit. So if you have one of those, how many potassiums did we have out of that? When it goes into solution, what does it do? It produces 3 potassium ions plus 1 phosphate. Right? So if the concentration was, what was it? 1.57. 1.57 molar of this unit, what's the concentration of phosphate? It's the same, right? 1 to 1. What's the concentration of potassium? It's 3 times that. 21, 2 and 15, 17, and 1 and 3 is 4. So it's 4.71 molar in potassium ions. So what's the concentration? What's the concentration of ions all taken together? Well, that'll be 1 plus 3 is 4. So you multiply 4 times that, or just add 1.57 to it. 6.28 molar in ions. Now, why is that important? Well, for chemists, the ionic strength of a solution often influences the course of a reaction. But if you're in the life sciences, or the health professions in particular, if you fix up a solution that's a certain concentration of salt, inject it in your patient, stick it in their veins, but you don't take into account the fact that it's dissociating, it will be, in this case, hypertonic to the patient. It'll cause their blood cells to go like that, and you'll kill them. So it's important to understand this concept, especially for health professions. What's the equivalent concentration of sodium chloride? Now I'm going to use not molar units because I can't remember what they are. But in percentage-wise, what would be isotonic to the human body's tissues? 0.9% in that. And I assume this is mass volume. Okay? So if you look at any intravenous solution that's going to be introduced into a patient, it will have equivalent to that concentration. In molar terms, taking into account ions and non-electrolytes. Okay. So like lactated Ringer solution is a complex mixture of things. But it will boil down to that concentration so that the solution is isotonic to the patient. I'm not going to spend time on this because it's the same discussion as we did for potassium phosphate. Which one contains the greatest number of ions? Well, what you have to do is say, well, if you have this molar concentration and that many, that volume, you can calculate the number of moles of that. Remember? Equals moles per volume. Well, we want to know moles. So solve for moles. N equals M times V. But this is supposed to be in liters, isn't it? And that's molarity. Well, guess what? If we're comparing these, the only thing that matters is we have the same units of measure. We could convert that to 400 mils is 0.4 liters, right? And do the calculation, that's fine. But save yourself some trouble. If you multiply molarity here times milliliters, what are the values? Millimoles is what you get. Okay. So if we multiply 400 times that, we get 40 millimoles. And this one we get 30. And this one we get 20. And this one we get nothing. Right? Because it doesn't, well, no, we do. Excuse me. I take that back. We get 80. We get 80 millimoles of the compound. But what's the number of ions? This one is 1, 2. This one is 3. This one is 3 plus 1 is 4. And this one is 0. Right. Sucrose makes no ions. So this is going to make 80. This is going to make 90. This is going to make 80. So this one produces the greatest number of ions. If I had time, I'd prove that to you. Which means, well, if you work that equation in reverse, if you know you have a certain number of millimoles and you divide it by milliliters, you have molarity. Millimoles divided by milliliters equals molarity. Right? Milli cancels milli. Moles divided by liters. Okay. We're going to skip that. Let's see. Dilution. Okay. When I was active, particularly in soil testing and plant tissue analysis research, particularly for soils, one way we would determine fertility of soil would be to extract the soil with a solution, usually some type of salt. But we would do hundreds of them at a time. And to make up enough solution on the spot would just be too much trouble. So we would make a concentrated stock solution of the correct ratio of ingredients. And then when we got ready to do the analysis, we just take a portion of that and dilute it down to the concentration that we wanted. So this is how you determine it. Actually, it would make more sense if we said M concentrated, volume concentrated equals M dilute times volume dilute. Okay? Now, why does that work? If you have a concentrated solution of this value and you want a diluted solution of that value, then this is the volume into which you're going to take some of that and put it in. This is the final volume at this concentration. So therefore, you take this concentration and you pull out an aliquot of that volume, dilute it to this volume, and you get that concentration. Now, why does that work? If you say this is the concentrated solution, and you want, we're going to use a volumetric flask here, whatever volume it happens to be, volume diluted. When we take a portion of this one out and we put it over here in this one, right? what changes and what stays the same? Well, we started here with this concentration, and now this concentration, this volume of the concentrate, we can determine molarity times volume equals what? Number of moles, correct? Okay. So what stays the same? Number of moles. The number of moles here is the same number of moles here. So this has to be equal also to molarity times volume. Well, we know the volume is here. So the molarity here is the one we want. So that's how they're related. Each one of these is equal to the same number of moles. That's why that equivalence works. And there again, it is an equation. So that means if you know 3 of those values, you can solve for the 4th one. So if we're going to dilute that concentrated solution, we know this one, we know that one, we know our final volume, solve for that one. That's how much we need to take out of the concentrated and dilute to this volume to give us that concentration. And if you do it enough, you do these calculations in your head. It's too much trouble to get a piece of paper out and a calculator. You just set it up so the calculation is easy. You do it in your head. Oh, I forgot I had this discussion. So this is the slide discussion of why it works. So I'm not going to labor that one any further. I'm going to skip this one too. This is the only one that would decrease the concentration of the salt solution. Add more water. The rest of them increase the concentration of salt. Or don't change it at all. What's the minimum volume of 2 molar sodium hydroxide solution needed to make 150 milliliters of 0.8 molar sodium hydroxide solution? Here we have a case of M concentrated times volume concentrated equals M dilute times volume dilute. So it's important when you're going to use this method that you identify which one belongs where. So which one's the concentrated one? Well, 2 molar. Which one's the dilute? This one. 0.8 molar. Okay. Where's the diluted volume? We want to make 150 milliliters. Okay. So now we have an equation and one unknown. And that was the question. What's the minimum volume of that concentrated one required? So you just solve it. And notice that if this is in milliliters, these molarities cancel, right? Because take it on the other side, one cancels the other. And then the answer is going to be in this units of measure right here. So you don't have to change it to liters. Just leave it in milliliters. Okay. 60 milliliters is what you need from the concentrated one diluted to 150 milliliters. And that will give you the new concentration of 0.8 molar. All right, types of chemical reactions. First thing I'll say is these are generalized. Some of them are very specific with how they're defined. Some of them are more general. And several of them overlap. When you have one type, it also may be another type to go along with it. So the 3 major types are precipitation reactions. And those are ones where you put 2 solutions together and they form a solid. the chemical reaction produces an insoluble compound that drops out of solution. That's the precipitate. Acid-base reactions. These are usually in terms of Bronsted-Lowry, which we haven't discussed yet. But you add an acid to a base, and you always get a salt and water. And oxidation reduction reactions. These are characterized by transfer of electrons. If there's no transfer of electrons in the reaction, then you don't have an oxidation reduction. But if there are transfers of electrons between species or atoms, then you're talking about oxidation reduction. And then other types, we can say combination reaction. We have two elements or simpler compounds form a more complex one. And then the other way around, where you break it apart, is decomposition. A single displacement reaction, where you have a compound of two components plus an element, and this C displaces one of those. Let's just say B displaces. So that's a single displacement. A double displacement, A, B, C, D. Now, since I've written it that way, that's the cation, that's the anion. So this cation combines with that anion, A, D, and this cation combines with that anion. That's a double displacement reaction. Then there's a combustion reaction. One of the reactants is always oxygen. Whatever else it's combined with, oxygen is always there. And also, if you have a combustion reaction, it's always oxidation reduction also. Okay, I mentioned precipitation reaction. Precipitation reactions are always double displacement. And they form a solid. One of those handouts is a solubility chart. Okay. So when you get, rather than memorize the rules that are at the bottom here, use this chart. And when you get a solution where you have ions mixed together from two sources, you check out the cation versus the anion, and you follow the cations across the top, and you find it, and then you drop down until you find the horizontal for the anion. And if that box is grayed in, then you've formed a precipitate. Okay. Here's an example, right? Barium nitrate is soluble. Potassium chromate is soluble. When you put them together, what do you get? Well, you get individual ions formed. Potassium, barium, nitrate, and chromate mixed together in the same solution, so they have access to one another. So which ones have affinity? Well, potassium and nitrate stay in solution. Right? They don't drop out. But barium combined with chromate forms an insoluble compound. And you can find that on that chart. Follow your barium across down to the chromate, and it's grayed out. So if a solid dissolves in a solution of an aqueous solution, we give it this next to the compound. Right? That means it forms aqueous solution. That's in addition to the other phases like S for solid, L for liquid, and G for gas. If it's insoluble, then we designate it with an S. Right? It may go in, the components may enter as AQ, but when you put them together, some of them may form S, form the solid. Now we have to say, it's like a qualification or a caveat. When we say insoluble, we mean mostly insoluble. There are degrees of solubility. And it's usually the case that when we say something is insoluble, it may be slightly soluble. But we're not going to get into that until later. In fact, let's see, do we do it this semester? I think we do later. No, I think it's the second semester. where we actually calculate solubilities. But for now, it's either soluble or insoluble. Just recognize that there's a gray area between. These are the rules, and they're on that chart. I would just point out, you don't have to memorize these, but I would point out if you're ever going to use this chart and you look at the solubility potential for products, and you've got two conflicting rules. Like your product has maybe rule 5 is operative, but rule 1 is also operative. They're set up so that the one above takes precedence, which means any of these down here, if there's a nitrate involved, it's always soluble. Okay, which of the following ions form compounds with lead 2+ that are generally soluble in water? But look at your chart. Lead and sulfide are insoluble. Lead chloride, they're insoluble. Lead 2+ chloride. Lead nitrate, soluble. Like I said, all nitrates are soluble. That's the easiest rule of them all. Number 1. And lead sulfate. Lead 2 sulfate is insoluble. And this one's thrown in as a joke. You know, a cation and a cation are not going to form a compound. Okay. Now, when we've got these types of double displacement reactions, where you've got free silver ions, free nitrate ions, free sodium and free chloride ions, this example, we can write this equation in its molecular format, or formula equation actually is more accurate, and balance the equation this way. This one is balanced the way it's written. Silver nitrate, sodium chloride, silver and chloride combine and form a solid. But the leftover sodium and nitrate, they're still aqueous. So if we write those in their true form and parse out all the ions, then it should look like this. Silver ions, nitrate ions, sodium chloride ions. And then the silver chloride is still solid. And then you've got sodium ions and nitrate ions. That's the complete ionic equation. Okay, you've got several examples of those in your review document to give you some practice. But notice also that in this equation, there's nitrate over here in the reactant side and nitrate in the product side. Right? I mean, we know they're there, but as far as the stoichiometry of the reaction goes, they don't matter. They're spectators. They're just watching the whole show. Sodium's the same way. It's there and there. Cancel those out, and what do you have left? You have the net ionic equation. This is where the action is. Sodium ion, silver ions combined with chloride ions to make silver chloride. That's the net ionic equation. Now, what's some practical advantage to that? If I wanted to conduct this reaction as a demonstration or as a lab exercise, but I find that I don't have sodium chloride in my stock, does that mean we don't do the experiment that week? No. Suppose I do have potassium chloride. I can still carry out that same reaction because potassium and the nitrate probably are spectators. They don't matter. This is the reaction I'm interested in right here. Okay. So this is an example. The formula equation, balanced. Then you split up all the ions and you leave the solid alone. Right? It's the same in both. And then you chop out the spectators and you have the net ionic equation. So you got to do this one first and get that balanced. Then you can walk your way through the other two. Let's see. These are steps for the stoichiometry of solution chemistry. Well, there's that chart I gave you. I just put it in here so you'd have another source. When you put these solutions together, 10 milliliters of this solution, right? You've got to be able to write the compound and write the compound for the reactants. And then what's the product, right? In this case, you don't need to know the product because you know it's a double displacement. You just swap partners, swap cations or swap anions. And that's what you get on the product side. Then you look to see, are any of them insoluble? Right? Most of the time, just one of them it forms a solid. Sometimes two of them form solid. Both of them do. Well, once you get your balanced equation, then you can determine what mass of the precipitate is formed because we know how to do stoichiometry. We can find out from this reaction how many moles of precipitate are formed, how many moles of that solid, and then we can convert it to mass. So how would you purify it? Well, if you let it sit long enough, it'll settle out and you just decant off a liquid. And if it's aqueous solution, then you dry it. But a more efficient way is to filter it. Right? You've got a solid, you need the right filter paper with small enough pores that it'll catch the solid and let everything else go through. And then you rinse it with something in which it is not soluble to get rid of all the soluble parts. And there you have a pure precipitate. Let's see. Here we go. What are the ions present? So these are all the ions. You just do a swap, right? Sodium and what? Phosphate. Sodium and nitrate. Phosphate and lead. Lead and nitrate. And you see, all right, which ones are soluble, which ones are insoluble. Right? I'm out of time on it. If you have to go, go ahead. Do I have time? Okay. So what's the precipitate? The only one that precipitates is lead phosphate. Lead 2-phosphate. So what's the balanced equation? Well, you write it out. You got this in aqueous solution, you got this in aqueous solution. It forms this one, and this one's soluble. And then you balance with your coefficients. Right? You've got all these polyatomic ions in there, so you can use those as balancing groups. You use balance the equation. What are the moles of reactants present in the solution? Well, you set it up so you know the volume and the concentration, right? So you can determine the moles. Right? And once you have moles, you can go anywhere. Right? So we have 3 millimoles of sodium phosphate here. How much lead nitrate do we have? 4 millimoles of lead nitrate. Now, when you have two reactants of definite amounts, one of them is going to run out. One of them is going to be limiting. So here's where you take one and you say, all right, if I have 3 millimoles of this one, then how much of this product will it form? And then you have 4 millimoles of that one, how much of that product would it form if it were all used up? And then the one that forms the least amount is the limiting one. And that determines how much you actually get. Okay, so here's where we do our conversion, right? This one converted all the way to lead 2-phosphate will form 1.5 millimoles. This one will only form 1.33 millimoles. So that compound is the limiting one right there. And this is all you're going to get out of it, 1.33 millimoles. Okay. All right. So that's how many millimoles of that solid are formed. If you need to convert it to mass, then you do have to convert back to moles. So if this is 1.33 millimoles, how do you do that? 1.33 times milli is 10 to the minus 3. There. Now you can convert to grams. All you need is molar mass of that compound. All right. Stole my own thunder. So I converted to moles and then used the molar mass. So we would form 1.08 grams of lead 2 phosphate. Okay. I'm going to have to skip this, I'm afraid, but it's there for you to look at. When you get to that point, you can pause the video if you want to look at it later. And this discusses the concentration. Then I will say that if the question is, what's the concentration of nitrate ions? Nitrate's not part of the reaction. It's a spectator. So you got the same moles of nitrate before and after. The only thing that changed is volume. So if you include the volume of the two solutions as your denominator, then you can calculate the new concentration of nitrate ions. But this one is a little more complicated because you did use some of, let's see, the phosphate. Some of it was used up, but that was the excess reactant. So you're going to have some phosphate left over. And to calculate its concentration, you got to figure, all right, how much phosphate did I use? And then subtract that from how much you started with. And then divide by the volume, and that gives you the concentration of phosphate, which is pretty low, actually. All right. Acid-base reaction. We're going to talk about this in more detail when we get to acids and bases. But the acid is a proton donor, which means when we were naming compounds, we always had the proton first, followed by something. This is the proton that's donated somewhere. It's donated to the base, and the base is the proton acceptor. So it could be sodium hydroxide, in which case this negative anion accepts that positive proton and makes what? Water. That's the product of all acid-base reactions, water. In addition, well, for those two, you have chloride ions and sodium ions. So sodium chloride is a salt, but it could be any cation or any anion. And in chemical terms, that's a salt. Oh, by the way, the net ionic equation for an acid-base reaction is always protons plus hydroxyls equal water. Okay. Let's see. Acid-base reaction. Really, for an acid-base reaction, you can approach it two different ways. You can use the net ionic equation, in which case you've got to determine how much of each one of these there are. Or you can use the molecular equation, or the formula equation. So let's say we're reacting aqueous sodium hydroxide. Let me get on this side so they can see it over there. Plus sulfuric acid. Right? So how would you balance that? Well, this one produces two hydrogens. That one only produces one hydroxyl. So you actually need two hydroxyls to make two waters. And then this is a liquid. And this is sodium sulfate, which is also soluble. That should be balanced. I like to use it this way sometimes because it just makes more sense to me. Both ways should work. But if you're going to go back to actual amounts of reactants producing certain amounts of product, then the formula equation is the only way to get there. Okay, what's a titration? A titration is delivery, in this case, acid-base titration. There are a whole host of different types of titration, but this is the basic concept. In this type of titration, you have a known amount of either an acid or a base, doesn't matter which, that you place in a receiver, and then you have a device that will measure out fixed volumes at your discretion. You control it, fixed volumes of the base or the acid, the opposite, whichever the case may be. And what you're trying to do is reach an equivalence point. That is where, in our previous example, where the exact amount of sodium moles, sodium hydroxide moles, equals the exact amount of required to neutralize the sulfuric acid and produce nothing but water and salt. That's the equivalence point, where the acid neutralizes all of the base or vice versa. And you can determine the equivalence point if you measure the pH throughout your titration and just draw your graph. Then the graph will tell you where it is. But you can't do that for hundreds of titrations. It just takes too long. Now, if you have automation, you can still do it. But if you have to do it by hand, it's more convenient to use an indicator that will change color when you reach that endpoint or get very close to the endpoint. So if you pick the right indicator, the endpoint should be very close to the equivalence point. It's not exact, but if you choose it correctly, the error is negligible. And we typically in this class use phenolphthalein as our indicator. If it's acidic, it'll be clear. And if it's basic, it'll turn pink. And you want that place where it changes. That's where the equivalence point is in there somewhere. Okay, so here's an example of, this is the overall equation. And we're saying how many moles of sodium hydroxide would be required to react with 1 liter of 0.5 molar sulfuric acid to reach the endpoint. You want an equivalence. You want the same number of moles of acid equal to the moles of base. But the trick is that sulfuric acid produces 2 moles of protons for every mole of hydroxyls. So you actually need 2 moles of sodium hydroxide to make the equivalence. So if we say 1 liter times 0.5 moles, that's 0.5 moles of sulfuric acid, which is 1 mole of protons, because there are 2 for every molecule. So you need 1 mole. You've got to neutralize 1 mole of protons, so you need a mole of hydroxyls. So you need a mole of sodium hydroxide. Wouldn't answer that question. Okay, I've mentioned redox reactions. It's derived from redox. Oxidation, let's do it this way. Let's use the, let's see, what is it, mnemonic device. Oil rig. Oxidation is loss. Anything that loses electrons is said to be oxidized. Reduction is gain. Anything that gains electrons is said to be reduced. And they always come in pairs. You can't have one without the other. It's the transfer of electron that matters. So what we're looking for is a change in the number of electrons in one of the species or the other to detect the movement during a reaction. Now, one way that you can use to identify an oxidation reduction reaction without actually determining the movement of electrons is there an element on one side of the reaction that ends up or originates from a compound? If an element goes into a compound or a compound produces an element, there has been oxidation reduction. And you don't have to do the calculations to say that this reaction is redox. Or if it's a combustion reaction, it's always redox. So in order to do that, we need some rules. How do you determine the oxidation state of an element? Well, if it's a pure element standing alone by itself, standard state, like it could be sodium metal, or it could be oxygen gas. The oxidation state of either one of these is 0 by definition. Now, the temptation is to say that looks like a charge because we're putting these values in that upper right-hand corner. Right? But oxidation state is a bookkeeping scheme. It doesn't necessarily mean charge, but it helps us keep track of movement of electrons. That's the only reason we use it. Okay, element. If you've got an ion, you actually do have an ion in the reaction. Then the oxidation state of that ion is the charge. So if it's a positive ion, it'd be +1, +2, +3. Or if it's a negative ion, it'd be -1, -2, -3, whatever the case may be. Oxygen in most cases in covalent compounds is given an oxidation state of -2. So for water, this would be -2 oxidation state. We know it's not an ion. How about the hydrogen? Well, that comes to, let's see, the sum of oxidation states equals 0 in compounds. So that means we've got to balance this with a +2. But each one of these hydrogens, you've got 2 of them, so each one has to be a +1. So hydrogen in this case is +1 and oxygen is -2. And that's the case for hydrogens in covalent compounds. In ionic compounds, I think there was one on the test. Was it sodium hydride? One of those. Yeah. If it's a hydride of a metal, say, yeah, sodium's good enough. Sodium hydride, this is +1 and that's -1. That's the exception. But in covalent compounds, hydrogen is +1. Oxygen. Oxygen is -2 everywhere except when it's a peroxide. So what's a peroxide? You have 2 oxygens put together and then something else out here. That's a peroxide. On your medicine shelf, you've got hydrogen peroxide. That's hydrogen peroxide. Actually, in your medicine cabinet, it's 3% by volume. If you want to make those volcanoes, adding potassium iodide to it, you need 30%. You can get that on the internet. They'll send it to you. Add a little colored, little dish soap, throw in some potassium iodide, and there it goes. Okay, halogens in general are -1, but fluorine is always -1. The halogens can vary depending on what they're bound to. And then the sum of oxidation states for polyatomic ions is the charge of the ion. Right? So if you have like PO4 3-, if oxygen is -2, then that's -8 total, but we need -3 out here. We got to keep that. So we really only need to balance -5. So phosphorus would be +5. Now you can check yourself, add them up and see if it comes out to 3 minus. Okay. Just follow the rules and you can balance these. Alkali metals, they're always +1 anyway. Oxygen's -2, so we can use these values here to calculate what this one is, the chromium, part of that molecule. This one has to balance to 2 minus. Oxygen is -2, so that means carbon has to be +4. Manganese dioxide, you would start with the oxygen, -2, and then calculate what manganese has to be a neutral compound. PCl5, the same. In this case, we have to assume that the chlorine is -1. It's a halogen. Otherwise, we can't calculate what phosphorus is. And like I said, this is a bookkeeping scheme. This doesn't mean that it has a charge. This is just the way we're tracking the electrons. And then this one is easy because fluorine is always -1, and then sulfur has to be +4. Let's see. I mentioned this already. What oxidation is, what reduction is. Oh, I didn't say this though. When something is oxidized, that means it is a reducing agent. Remember, they always come in pairs. So if I'm oxidizing, I'm losing electrons. That means I'm causing reduction of something else by transferring my electrons. And conversely, if I'm being reduced, that means I'm oxidizing some other element or compound to extract electrons from it. Okay. Which one of these is oxidation reduction, and identify the oxidizing agent, the reducing agent? This one is a redox reaction. Notice there's an element here, and it's in a compound there. So we know that one is. Here we have a compound, and there's an element. So we know that one is. If we do the calculations here, we find that this is not a redox reaction. Right, so we're only interested in these two for oxidizing. This one is 0. That's an element. This one's 0. That's an element. This one's 0. Right? I do the elements first because they're really easy. Chlorine is going to be -1, so this one has to be +2. And this one's going to be -1, and this one's +1. So what happened? The hydrogen went from +1 to 0. How do you do that? You have to add an electron, don't you? Add an electron to a positive, and it makes it 0. So this one is a reduction. So where's the oxidation? We know they come in pairs always. So we have to go from this one to this one. To go from 0 to +2, it had to lose 2 electrons. So this is the oxidation. Okay? So if this one is being oxidized, it has to be the reducing agent. And if this one is being reduced, it has to be the oxidizing agent. Okay? Now this one is kind of weird. I'm glad that this one's in. Notice you've got one reactant over here and 2 products. So how do you get oxidation reduction out of that one? Well, notice there are 2 of them. One of them is the oxidizing agent, and the other one is the reducing agent. Right? So one of these, this is +1, +1. So this one goes to here at +2. It gets oxidized. And this one goes from +1 to 0. It gets reduced. This is called a there we go. A disproportionation reaction. And it's typically used in this reaction in particular is used in the smelting of copper ores. All you have to do is heat it up and you can extract copper from it. And then they probably take this one and do a different reaction to get the other copper out. Okay. So this is one of those balancing schemes where if you've got a redox reaction, you want to take advantage of the fact that electrons are being transferred and balance the electrons first, then finish it off. That's what all that says. So if we balance the reaction between solid zinc and aqueous hydrochloric acid to produce zinc 2 chloride and hydrogen gas, right? What do we have? Well, we know we have individual ions here. We know that's a zero oxidation state. That's a zero oxidation state. This one's a -1 and that's a +1. So we can tell which one does what. Right? So we've got our oxidation states identified. Now we'll say, here we have 2 electrons lost. And where are we headed with this? If you lose 2 electrons from one place, you got to gain 2 electrons someplace else. The electrons have to balance. So that's why we do them first. Yes? Huh? Oh, yeah, I'm not finished. There's more. This was 1 electron gain for each hydrogen, but there are 2 hydrogens. So we need to double the number of hydrogens. We've already got 2 here, so we need 2 there, don't we? So let's draw this again. Times 2 means that we need 2 of these, right, to give us 2 hydrogens. Now the electrons are balanced. Let's see if the rest of the equation is balanced. There's 1 zinc, 2 hydrogens, 2 hydrogens, 2 chlorides. Ah, we need a 2 here. Oops, sorry. So now we have our 2 there and our 2 there. And actually, this is all we need to do. That's balanced. But sometimes you get the electrons balanced, but the rest of the equation is not balanced. Once you get the electrons balanced, then you can set up your the budget, like I showed you earlier, and finish it. But this is a simple one that balanced itself with just the redox. Okay, that's it. And I'll do what I said with the lab discussion and post that discussion in your 103 course.